So given a homomorphism, here is a very important concept. Take all those elements in the left hand side such that the images are the identity of the right hand side. Can you see that this is a subgroup of G prime? Huh? Can you see it? That is a subgroup of G prime? You have to use this. If phi of A prime is E, phi of B prime is E, phi of the product is also E. You can see it is a subgroup. It's also easy to see it is an invariant subgroup. Exercise. So this is an invariant subgroup. So the moment you see an invariant subgroup, you do this quotienting operation, G prime quotiented with respect to K. How is this related to G? Well, the answer to that comes from the second of the four possible interesting relationships between two groups. I said there are four of them. A is done. The properties of this quotient lead us to B. The concept of an isomorphism between two groups. Again, G prime is given, G is given. Isomorphism is a very special case of the automorphism when phi is 1-to-1 onto and invertible. So, sorry?
When you say automorphism, you mean homomorphism.
Oh, sorry, I beg your pardon. Yeah, there's a mistake. The video cannot be corrected, no? Homomorphism. I did not mean, I made a mistake. It's an example, a particular case of a homomorphism when phi is as nice as it could possibly be and it has all these properties. Then we say that in this situation, as groups, there is nothing to distinguish between G prime and G. We can say they are, from the point of view of group theory, they are really identical. They may not be identical in some physical context. You might have, after all, you can have a group of rotations in physical three-dimensional space. So that is a property of three-dimensional space. You can also have a group of rotations in isotopic spin space. Some of you may be familiar with it. As groups, they are the same, but physically they are not the same.
You began today's lecture by saying that Srinivas wanted the multiplication table to be right. So probably will say that they will have the same multiplication.
Exactly. Yeah, I wanted it to be emphasized. Yeah. So if there is an isomorphism between two groups, we can say as groups they have the same structure, and the multiplication table for one of them leads automatically to the multiplication table for the other, and vice versa. They are on the same footing. So this is a very simple idea, and this isomorphism is what is involved in the previous construction. If you take a homomorphism, there will be a kernel. What does this kernel measure? It measures to what extent is phi many to 1. To what extent is phi unable to preserve differences between elements of G prime. This is measured by the kernel. Once you take this quotient, then the quotient is isomorphic to the right hand side, where for definiteness I have assumed that the homomorphism is on to.
That thing it is measuring only for this this identity element in G.
Yeah.
What about other elements?
Problem. So you can easily verify. Suppose I have two elements in G prime which have the same image. A prime and A double prime both have the same image in G. What can you show from here? A prime and A double prime differ by an element of the kernel. A prime, A double prime inverse is in capital K. So we define it so that it tells you what are all the elements in G prime which get mapped into the single identity element. The same construction will tell you when is it that two elements in G prime share a common image for any pair. Okay? So it is the same kernel.
Can I add a comment?
Yes, please.
You have been talking a lot about imaging.
Yeah.
In the real imaging also, this channel is the resolution limit.
A limit. Yeah,
That's
sure.
what will appear as a point.
Yeah, sure. Very good. Very good.
Here, if the order of G prime is less than G1, then what will happen?
Order of G prime less than G.
Yeah.
Then this cannot be ever satisfied. I am assuming this for simplicity. If this G prime has 10 elements and G has 20 elements, at most phi of G prime can have 10 elements. In fact, it may have less also.
I forgot that.
Beg your pardon?
I forgot that condition.
Yeah. So this simplifying assumption is made in making that statement. So to wrap up, in a homomorphism, the two groups are on a different footing. The homomorphism is from one group to another. It's from one in the direction of the other. So they are not symmetrical. In an isomorphism, the situation is symmetrical between the two groups. And it is clear then in an isomorphism, G prime and G have to have the same number of elements if they are finite. Even if they are not finite, there has to be a one-to-one correspondence between elements of one and elements of the other. Okay. Third construction involving two distinct groups is the concept of the direct product. I would like to finish these four operations. It is like finishing in the last over like yesterday, so that tomorrow we can start a new thing. Now I will just change my notation a little bit. Pardon? You said something?
Don't lose the maths.
Yeah, it's not in my hands. You will know in November. Suppose two groups G1 and G2 are given. All right? So then we define a new group which is called the direct product. Now this is such an elementary construction that I will essentially leave it in the form of words. What are the elements of the product G1 cross G2? They are ordered pairs. And what notation shall I use? I will write A1, A2. A1 is an element of capital G1, A2 is an element of capital G2. And you pick them independently. Then you take another such pair, B1 and B2, and you just define the multiplication to be A1, B1, A2, B2. Each group minds its own business. Inverses also follow a similar independent law. That is to say, the inverse of the pair is the pair formed by the inverses. And you can check that in this sense, G1 direct product G2 is also a group. This is a very simple construction. Given any number of groups, you can take their Cartesian product in this way, and you will get a product group. And what is the order of G1 cross G2? Yeah, the orders multiply. So this is extremely elementary. The last thing I want to do today, which will then mean a clean completion of ideas, is what is called a semi-direct product. Now this is quite sophisticated. Here again, what is given? A group G1 and a group G2. The construction of a semi-direct product, it goes like a direct product, but at a certain point you put a twist into the construction. Now I have always difficulty with the notation for semi-direct product. Does any one of you know what's the accepted standard notation? I just don't know.
You can set these standards.
No, you have to look at books and see what they generally write. I have been a bit lazy. I don't remember now how it is written. I just invented this for my notes. There might be a simpler notation. I just don't know. Some modification of the ordinary cross product. But it's a very delicate, very sophisticated construction. What are the things needed to form the semi-direct product of G1 with G2? First of all, let me tell you, in the direct product, the two groups again play very symmetrical roles. Whether I write, formally speaking, G1 cross G2 or G2 cross G1, there is no real difference. One is what? Isomorphic to the other. In a semi-direct product, they are not on the same footing. So what are the requirements that you must start with to go through this construction? You have to say the following. For every A1 in G1, we need an automorphism tau A1 of G2 to G2. Now automorphism is something I have described a few minutes ago when we were talking about operations within a given group. So I remind you what I said 30 minutes ago. An automorphism is a one-to-one onto reversible mapping of a group onto itself such that products of images go into images of products. That was an automorphism. Now what am I requiring? I am requiring many automorphisms of G2, many mappings of G2 onto itself. I am requiring one such mapping for every element in G1. So what I am requiring for this construction to come is that this first group must act on the second group by a family of automorphisms. I also require that these automorphisms compose properly. Please discover for yourself the meaning of this equation. Tau A1 prime is a mapping of G2 onto itself. So you can apply it. After having applied it, you apply tau A1, another mapping of G2 onto itself. The composition of these automorphisms must be automorphisms of the product elements. So the first group must act on the second group in a sensible manner. It must map the second group into itself. It must preserve multiplication law in the second group, and the automorphisms themselves must follow the multiplication rules of the first group. So this is why it is a very involved construction. And now comes the definition. What are the elements of the semi-direct product? They are written in the same way as in a direct product. You just take the Cartesian product of G1 and G2, take ordered pairs. Sorry, this is not a good notation. A1, A2. Sorry, this is a mistake. A1, A2. A1 is in G1, A2 is in G2. And then you take another ordered pair, B1, B2. The composition rule in this new group is quite delicate. As far as G1 is concerned, it minds its own business. It is exactly as it was in the case of a direct product. But when you come to the elements drawn from G2, the entry here is not just A2 times B2. It is something more involved. It is A2 tau A1 B2. This is the composition rule for these ordered pairs. So there is a way to, as a mnemonic, to remember this. You allow the elements of G1 to mind their own business. When you come to the elements of the second group, it is not A2 times B2, but A2 times the effect of A1 on B2. So that is how it has to be written. This is called a semi-direct product. It is also a group. This is very important for you to confirm. So this is, I can certainly say, if it's the first time you are meeting it, it is really non-trivial. Make sure that by this definition, we do have a group. You must make sure that this composition rule given here is associative. You must make sure there is an identity element. You must make sure there are inverses, all with the proper algebraic properties. Everything must work. All the laws of group structure must be satisfied. And in confirming all that, you will find this has to be used. The automorphisms on G2 given by elements of G1 must themselves behave properly. They must compose with one another according to the structure of G1. They must, each one of them, preserve the structure of G2, and so on. So this is quite an involved construction. But,
You have to define some kind of action of
beg your pardon?
You have to talk about
Some
some kind of action
kind of
action of G1 on G2.
action of G1 on G2. Yeah, that's what for every element of G1, we need an automorphism of G2 onto itself. So this is the sense in which elements of G1 act on G2.
It's not clear how the automorphism
I can't make out what you're saying.
It's not clear to me how that automorphism depends on the elements of G1.
I'm demanding it. I'm saying for each element of G1, please find some automorphism of G2. It may be different for different elements. But they cannot be arbitrary. They must compose with one another according to this rule. So you're putting a lot of conditions here. Before a semi-direct product can be defined, what you need is a whole family of automorphisms of G2 onto G2, one for each G1 element. And they must behave properly with respect to one another. If all this is given, if you can satisfy these conditions, then and only then this is a valid group composition law. And you must verify that if you want this to be associative, if you want it to have a good inverse for every element, if you want it to have a nice unit element, identity element, these conditions are needed. Can you see in what way a direct product is a trivial case of a semi-direct product? All taus are identity. Okay? So you see in what non-trivial way one has gone from direct product to semi-direct product. So to clarify what you said, all this is to be given before you can construct a semi-direct product. So there is no question of verifying them later. You have to be given in advance. If you don't know tau A1 for all A1, or if they don't obey this composition law, this construction cannot be done. It will not be a group. Now once again, semi-direct products are very common in physical situations. Let me just give you a trivial example so that you don't go away thinking that I could have omitted this idea. consider the group of rotations and translations in a three-dimensional space. Rotations and translations. You know the name of that group? Three-dimensional space. Much older than Poincare. Euclidean group. Now, the Euclidean group, rotations and translations, it has a subgroup of rotations about a fixed point. It has a subgroup of translations. These are two subgroups. The Euclidean group is a semi-direct product of rotations by translations. Now, I don't know the language where you say what by what. Anyway, G1 plays the role of the rotations in the Euclidean group. G2 plays the role of the translations. Why is it not a simple direct product? Why is the Euclidean group not a simple direct product? Please, you can do. We will do it in late November, sure. But you can easily sit down and calculate. If you describe an element of the Euclidean group as made up of a pair, a rotation and a translation, and you see how the combination affects the coordinates of a point particle, and see how one element of the Euclidean group and another element, how they combine to give a third element, you will see you are dealing with a semi-direct product, not with a direct product. Okay, so this in advance, just to see for yourself the importance of this construction. And naturally also this will extend to the Galilei group, it will extend to the Poincare group. In the case of the Poincare group, G1 would be all what? Analog of rotations. What will it be? Homogeneous Lorentz transformations. What will be the G2? All space-time translations. The Poincare group, which is basic for special relativity, is a semi-direct product with homogeneous Lorentz transformations in the G1 slot, space-time translations in the G2 slot. And so that also requires this concept. So this is just to reassure you, it is not a luxury that we have to introduce this idea. We will use it later in physical ways. So I stop at this point. I have gone a little ahead, but it is a good place to stop, because tomorrow we will start with representation theory. Okay.